Hi, everyone. My name is Jamie Soto. I'm the Technical Director of the Metabolic Phenotyping Core Facility. I've worked with Dr. Dale Abel for about 15 years, and I've been running this core since we moved to Iowa about 7 years ago. So today I'm just going to go through a list of our services so you guys can get an idea of what we are about. And I'm going to start with talking about the Seahorse XFE24 that measures mitochondrial bioenergetics. So the Seahorse is optimized for use in cell culture, isolated mitochondria islets, or small tissue samples. So what it does is it measures simultaneously oxygen consumption rate, or what we call OCAR, and extracellular acidification rate, which we call ECAR. Excuse me. OCAR, is measured by the consumption of oxygen through respiration via mitochondria, and ECAR is measured, it measures the change of pH in the media. This is a close-up of the wells and the sensor of a Seahorse plate. So what happens is this sensor is lowered to right above the cell layer, and then measurements are taken, and then the sensor is raised and is brought back to baseline, and then it repeats these measurements. There's 4 drug injection ports per well, and these are used to deliver inhibitors, stimulants, substrates, and other compounds to the wells for the assay. This is a busy slide that I'm really not going to go over, but I wanted to just show you that Agilent has quite a few pre-made assays available to use with the Seahorse, and the most common one that is used in my core is the cell mitochondrial stress test. Another machine that measures mitochondrial bioenergetics is the O2K from Ouroboros. We have 2 of these machines, and they each have 2 chambers here, so you can measure 4 recordings at once. And this system is great for use with saponin permeabilized tissue fibers and isolated mitochondria, and even some cells if needed. It depends really on what it is you're trying to do between using this one or the Seahorse. This is just a sample tracing from the O2K. The blue line here is the oxygen concentration in the chamber, and the red line is the slope of the blue line. And this is just a list of example of some substrates and compounds you can add to the system to either stimulate or inhibit respiration, depending on what it is you're wanting to measure. So I'll move on now to talk about our NMR service. So this measures whole body composition without anesthetics in mice and rats in under 3 minutes. It specifically measures fat tissue, lean tissue, and free fluid. We have 2 machines available for use. The LF90 is for larger mice over 50 grams and for rats, and the LF50 is for mice only up to 50 grams. The next service is our whole animal energy expenditure. What this is indirect calorimetry, and this is a non-invasive measurements of food intake, energy expenditure, respiratory exchange ratio, and physical activity. We have 2 different systems that can do this. The clams has special housing. This is what the cage looks like. So the mice are in here and they're suspended on this flooring. There's holes in it so urine and feces fall through to the bottom of the cage. And then the chow is offered in a powder form here in the middle of the cage. And that sits here on a scale to measure the food intake. The Promethean, this system is newer to us, and it looks a lot more like a home cage where there's bedding here on the bottom, and the food is standard pelleted chow offered here. And there's other differences to these systems, but I'm not going to go into those details now. If anyone has questions or if they're ever interested in using this system, I'm happy to go over the differences with them. Okay, second to last is the glucose tolerance tests and insulin tolerance tests. So GTT, typical assay, we fast the animals for 6 hours and then we give them a bolus of glucose, and then we measure their blood glucose levels at these time points. Optionally, and which usually goes hand in hand with the GTT, we can collect plasma at time 0 and 30 for insulin analysis at those time points. An ITT consists of a brief fast, then a bolus of insulin, and then we measure the blood glucose at these time points. So a GTT is going to tell you how glucose tolerant your model is. And in this example, you can see that the closed circles are less glucose tolerant than the open circles. And an ITT is going to tell you how insulin sensitive your model is. The closed circles are less insulin sensitive than the open circles in this example. The last and most complicated service that we offer is the hyperinsulinemic euglycemic clamps. So what is a clamp? Clamps assess whole body in vivo insulin action, and they're considered to be the gold standard method to assess insulin sensitivity. There's 3 types of clamps that we offer as a core. The first is the most basic, or is the basic hyperinsulinemic euglycemic clamp, where insulin is infused at a constant rate and glucose is infused at a variable rate to maintain euglycemia. The second type of clamp we offer is a traced hyperinsulinemic euglycemic clamp. This clamp is the same as the first one, and it's the most popular one we offer. The difference here is that we infuse radioactive tracers to determine specific tissue uptake and to track glucose disposal. The last type of clamp we offer is the hyperglycemic clamp, where we infuse glucose only to maintain hyperglycemia, which measures insulin secretion response. Some things to keep in mind when designing a clamp. Each clamp is individualized to the investigator's needs. Mice should be age matched with the same background strain, and it's best to use litter mates if possible. Depending on which tissues you're interested in, the insulin dose is important to keep in mind. For example, if you're looking at skeletal muscle, a higher insulin dose is needed. The duration of the fast is something we leave up to the investigators, but we do recommend a 5-hour fast. That's fairly typical. The most important thing to remember is that there's a surgical or catheter fail rate of about 15%, and that's actually pretty good in the industry. So we recommend a minimum N of 6 to 8 per group to offset any surgical deaths or complications. And this assay does take a long time. It can take 2 months to complete for 2 standard groups or longer, and that's from the beginning of surgery until the end of data analysis. So this procedure takes a lot of planning. So if you're ever interested in doing clamps, be sure to reach out to us very early on in your planning stage. This is what a clamp setup kind of looks like. So in this example, they're using the carotid artery to sample blood. We're working on getting that up and running here in our core, but we're not quite there yet. Over here, you've got tritiated glucose, donor blood, which is only used if you're sampling through the carotid, insulin, and cold glucose, all being infused at the same time through the jugular vein. There's also a bolus here for deoxyglucose tracer if it's being used. Mice are awake and allowed free movement in a small cage during this 2 to 4 hour assay. And the only time they're handled is when we're sampling the blood, which we currently do from the tail. This is just an example of what clamp data can look like, some basic clamp data, and this is from the Norris lab here on campus back in 2014. So here on the left, we have the blood glucose levels, and you can see at the beginning of the clamp, the measurements are kind of rocky and all over the place, but towards the end of the clamp, it levels out, and this is what we call steady state. On the right here is the glucose infusion rate, and similar to the blood glucose, it's rocky at the beginning, depending on your group or on your model. And then towards the end, we have steady levels again. So that's pretty much it. Those are the services we offer. I do want to point out that Wojciech and Kyle work with me here in the core, and they are the masterminds behind our glucose clamps.